So people assume. So suddenly we have this whole like.
These guys from mirror to the zero ring, they don't have to be exactly right on top of that, right? And the position of the zero ring on C star would choose where you're putting that circle.
Right. So
you're just someone drawing them all.
Right. There are different versions. So here we're looking at exact Lagrangian with fancy local system on it, C-star local system on it. I could do a different version. I could not requiring this being exact. Therefore, I can draw the circles at different phases, and then I require the local systems like the U1 local system, and then if I consider non-exact Lagrangian versions without fixing any exact structure, these two descriptions are equivalent. We are creating the area between these two as some non-unit, non-modular. Okay, so this T can be thought of this. So how do I compute it? We compute this T by wrapping this guy near the boundary. And compute this guy at this. Okay, and you spawn there are intersections with itself. So they're labeled by all the integer points, and this as a vector space is just summing up over all the intersection points. It's E0, E1, and the composition tells you that this En, you compose them equals to En plus N. So this behaves just like En times Cn equals to E plus. Okay, so we show that it has the same vector space structure and the right set, the same algebra structure. Right. Okay. So how do we show actually this equal to that? We say that this object T is sort of like know it all because it can fill all other Lagrangians in this game, in this T star S1. So I didn't tell you precisely what does that mean, but the idea is like by wrapping every other Lagrangians can be every other Lagrangians and every relations between other Lagrangians can be witnessed by this T Lagrangian. In that sense, knowing this object T equips to know everything. So this is like a genetic by harming T that is entity mountain. And then you show NT equals to this algebra, then you're done. So that's like one strategy or one example. So this example has another interpretation, which is about Tauer's migration. You may have heard about the slogan that homological mirror symmetry is about T duality, which says that this star and this star S1, they both average over R. So here you can send Z to the log of the modulus T. Here you can just take the projection in the row and just map it to not part of rows like P. So P is a temporal fiber coordinate. So here the fibers are Lagrangian powers. Okay, so in general, you can also play the same. For example, if you have some compactification, the P1 compactifying the C star, and here you would include T star X1. But in this game, you somehow do not compactify. You do not compactify this end. As physics language, you are trying to make the circle infinitely large. How to make the circle infinitely large? You can say, okay, you can put it back here. Just say, instead of going around the circle, can go back to itself. You see, you never go back to yourself because it takes an infinitely long time to go back to yourself. So that's one way to say you're saying break the circle to make a hole. Another way to say it is like you put a stop at a boundary point. When you put a stop at a boundary point, what happens is that originally you have some periodic flow on boundary, but now this flow will never be able to go past this stop. So it takes a long time to go back. So that's the idea you want to stop. Now, the spectral sheet O0 will correspond to certain Lagrangian. You can try to compute that this Lagrangian has to be just right stopped by the stop. I can't draw it. Maybe I can draw it this way. And draw it periodically. So here is like the X1 direction, here's the R direction. And I'm drawing things vertically. I'm drawing things like I found graph the X1 direction. And then the flow on the boundary will be this way and this way. So you see that if I try to flow this blue guy, I get immediately stuck by the stop. I don't flow very much. I only have one intersection. So corresponds to like of this guy is like O0. It's also the of this it's called this L. And you can consider what happens if you have just a more complicated line models here, like O1. And then you would have some Lagrangian looks like this. Sorry, I perhaps produce this O minus or O1. You can imagine that you have more twisted Lagrangian on the AA side that corresponds to some line models that have more curvature. Okay, so I didn't do quite justice to this last subject, but given the time, I can only say these words. Maybe the key concept, the key takeaway here is that we're trying to prove categorical equivalence. We're trying to match object to object, arms to arms. And the way to do it is to try to find generators on both sides. So that the generator are certain kind of a special objects that are like the boss in the category that knows every other guys in this category. And if the boss has certain the same endomorphism algebra, you can compare them, then you are good. Here, a mental conceptual puzzle for me sometimes is that these two approach, one approach using T duality, one other approach is using this generator. I think they are not always like obviously related to each other. For example, in the story, we are going to tell, I don't know how to tell the T duality story. So if the audience has such expert, no, I'm happy to discuss after the. Yeah. There are some hints of T duality here, but how to pin down what's exactly going on.
And maybe you want to say that this sort of rules of how you allow to graph and where you have to stop, that's encoded in superpotential and ambiguity model.
Oh, yeah, exactly. Yeah, I forgot the notion of the stop. So I'm just also so compactifying on P side Oh, for those who know, like whenever we do the complex geometry or potential category, we call them B side, and the synthetic side we call that the A side. I guess this historical business paper event. So kinetic on the B side space corresponds to let me just say what I did. I stop on the B side space group. It also is equivalent if the A side space it happens to be a complex space as well. It's equivalent to add a superpotential. Superpotential W. Let's call this space. Let's call it this one. So previously we have a C star. Its operation of C star is like mirror to category of C star. Identifying C star with C star S1. And you can see now operation of T1 is equivalent to category of the same space C star. But we add potential, say W is U. So potential the U is like 1 over U. And we require that the Lagrangian to when you have a non-compact Lagrangian goes up to infinity, you won't require that the W to be totally to be either like real have certain growth condition, growth condition towards the end. So this moment, just draw this picture in the W plane. If you map C star U by this U plus 1 over U, end up with 2 critical points, and then the shadow of the Lagrangian you are drawing can be made to have this next shadow, which we call the dimple, and these dimples. One corresponds to O0, one corresponds to O1, and the sum of them, they are generators of the category. So one way to produce generators in some setting are trying to construct this kind of dimples. Okay, but that may not always work. Your B side space is not projected. Okay. Yeah, so that's like homological mirror symmetry, which I have been working on for some simple spaces like toric varieties. This is the first time I go beyond toric. I work with some non-Euclidean spaces. I mean, spaces come from some non-Euclidean the GIP or constructions. The second thing I'll talk about is sort of a 3D Coulomb branch. So I'm going to say something in words, not writing down anything about the physics part. It comes from 3D equals to 4 theory, where consider moduli space of monopoles or singular monopoles, moduli space of smooth monopoles, moving in the background, perhaps with some singular monopoles. So the physics origin of this story is very important, because once you understand the physics origin, you can do a lot of generalizations to it. Like you can talk about like a deep yeah, like you can do various more generalization of the modular space problem we are considering. But here I'm going to just the black box all that physics theory. I'm just going to tell you about the more mature, like translated into math story, which is like the PFN story, the mathematical application. Right? So it starts with PFN, which is a technical word and the college. Which considers which considers what's called pure gauge theory. So the general, sorry, worked by Lagrangian and then later by government Informal, and then this first paper. It's 2001, and this is like 2015 or something. Maybe the first one was 2003 or 4. Okay. Yeah, around that. The second one is 15 or 16. 15 or 16. Yeah. So it's like G, and then it goes to 0. So I mean, what do I mean by G? So G, so input of the story is G is a backend loop, and then is some representation of G. So secretly, what we're doing is that we're going to consider a quadrilateral representation or some representation where G has some potential bundle of its target, and choosing a plane is like choosing a polarization. So if you wish, you can always start with C to start, let me say equals to 0. It's already that input and output.
I will not maybe hold the other board down, but one different other.
Yeah, I really want someone to stop me if there is anything like that. I go very, very fast, and it's not like it goes against the title of our seminars, like informal.
Yeah, no, the second one is informal. The trouble is about outwards, but the only thing we have diagrams. But now you have thoughts. But typically, I would fill in the questions. Please go ahead.
Yeah, usually I'm in the audience, so like I'm like playing the idiot's role to ask the questions like
I don't need to start.
So so here's the input. Input is just simple. You have a group, you have a representation. Output. Well, there are various versions of the output I could say, but let me say the simple way. There are and we can consider basically Coulomb branch, the additive or multiplicative Coulomb branch, or the cKLRW Coulomb branch. Anyway, so so we have a MC Gn. This is defined by this first. You consider. I'm just going to write down something that using fancy notation. But conceptually, this thing can be made reverse. Where here the O is this this our series ring, and this K is this our series, and the carbon picture is like you have space X, let's say sits inside Y, and you want to consider the certain homology theory of this space. So it has a convolution product. And that makes this algebra into an algebra. And yes, yeah, this is going to be a homology. Oh, yeah, right. So far, all writing, just take a grain of salt. But if you want to, yeah, it's like only true at the idea level. Right, so basically it's just like a matrix multiplication. If X is a bunch of points and Y is just a point, then it's literally just matrix multiplication. And here X is just some space to compensate like points in that space, you have to say a homology cycle in that space. So you can do convolution product. And I'm not going to explain what this normal GOR they are stacks, which myself I'm not familiar with, but at least has the shape of a convolution. And while we have this, we're just doing really gauge theory, and why do you give me a normal GO? That's because I'm just have some simple aside. For this input data, you could do some really TFT where like just writing some naive expectation. If I give me some 3D TFT, if you input for me a three manifold, say close three manifold, I'm supposed to get a number. But maybe it's not going to get a number, maybe it's not finite, I have to use a polynomial to represent that guy. But if I input the S2, a two-dimensional sphere, then which is the S2 can be thought as just a S2 with certain framing, but as a three manifold with certain thickness, then I should get a algebra. The vector space. That's algebra structure. The algebra structure comes from various ways you can stack together these two guys and merge it into a big sphere. And as this S2 comes into this, the S2 can be also allowed. You are gluing two disks along the boundary. And here are the two disks. The stack of both like infinitesimal disk and stack of K is like the boundary of the disk. So we are trying to glue disks along the boundary. Okay, so again, I'm not an expert in this TFT story, but this is something that makes sense. So this is so-called additive Coulomb branch. And if you want to consider the so-called multiplicative Coulomb branch, you have to replace this Graham homology by K theory, which I'm not going to explain here. But I'm going to explain to you some example where I have the so-called pure gauge theory. Suppose you're telling GLN, I can tell you very explicitly what these two spaces are, additive and multiplicative. I'm going to give you two examples.
But anyhow, we're just trying to produce the algebra for one function, right? Whichever way we do that.
That's right.
The
There's also similarly like if you don't have matter in your story, pure gauge theory, you end up with some nice smooth affine space. I mean affine variety and smooth. the moment you start putting matter into it, your space usually will become singular. And then there are two ways to make it non-singular. One way, which you'd like to do on the side, is to take resolution, where you end up with something that's not affine anymore, but has interesting coherent shape category. The other operation which you can do is to do deformation, where you still stay within the affine world. And you like to do like a set on that space, you do category to that affine, smooth affine provided. And the two choices, deformation and versus resolution, they are sort of related to each other. And our mirror symmetry statement would be like coherent shape on this result that I'm able to category on that deformed factor, some extra data.
In fact, for Coulomb branches of 4-dimensional gauge theory with a circle, it's literal. The mirror symmetry uses the Coulomb branch of the 4D gauge theory of a circle, complex structure deformation to Coulomb branch of the same gauge theory of a circle. Yeah. So 4-dimensional gauge theory of a circle, the statement of mirror symmetry is very simple.
Okay. Yeah. So
expect much, but it's
yeah. So let me just give you some examples. So G equals to GL2 and N equals to 0. The additive
being for the 3-dimensional gauge theory. Sorry, for the 3-dimensional gauge theory.
Yeah.
Not 4-dimensional gauge theory.
Yeah, so far everything's like really I don't know what to say is important. So it's going to have a coordinate ring of C of so it's going to be invertible variables here and 1, 2, and then some ratio variables. Under the S2 action, which permutes the index 1, 2. Okay, so this is C, we're turning x1 plus minus, x2 plus minus, y1, y2, and U being the x1 minus x2, coded by y1 minus y. So this can be also written in a succinct way for a scheme of 2 points in C1 of C star x, where you take the so-called horizontal part. Okay, what do I mean by the horizontal part? So I'm only going to draw things in the picture. So I'm having a trivial bundle for the base C1 fiber is going to be C star. Okay, it's 2-dimensional complex space. And I'm considering a moduli space of 2 points on the space, roughly speaking 2 points. And if I just consider that, then you would say, okay, how about just taking the symmetric points, symmetric square of this space? Well, that's the first guess, but this guy is not smooth. It is singularity when the 2 points coincide. To resolve that singularity, you blow up the diagonal here. That means you remember not just the fact that they coincide, but remember how they become coincide, like in which direction they come close together. Okay, so that's like the full cube. Well, I won't give you a definition for cube. These are just like abstract algebraic definition where you say you take some ideal in that structure sheet, of C plus C star, and you also quotient of that structure ring by ideal to have length length 2. Geometrically, this thinking. So the horizontal part means what? Means that when you have 2 points, we have the 2 points moving here, you want their shadow to also have plus 2. Also have plus 2. That means, first of all, you want to delete those points, separate points where they're leaving the same fiber. And also you want to delete on the diagonal that. You want to delete on the diagonal that when they become coincident, you want the slope to not to be vertical, and the slope to be somewhat like horizontal. 2 points come here. That is okay. We have 2 points come together. But you do not allow them to come together like with the slope, with a vertical slope. So the horizontal part, sometimes you know that by removing y1 equal to y2 over transformation. It means that if you do not totally forbid y1 equals to y2, because you only forbid those proper transformation. Okay. At least some version of the explanation makes sense, I hope. And to reflect the fact that when I take blow up, I take one patch of the coordinates and blow up the dam. All right. And you can also have this multiplicative branch. Where I denote by a little multiplication sign up here. This is roughly the same, except now I allow my y1, y2 also to be vertical. I mean, this y1, y2, they previously they are called as like homology class, but now they should be called as K-theory class. So the denominator better writing is the 1 minus 1. So it can be also thought as the taking horizontal part. Star y plus the stars. Now I'm going to be able to state the homological mirror symmetry statement for this space. Let me just state a statement for the pure H theory. This will be like potential. B side we will put and C is 3,000 and 0. I can tell you what external space is, but you can imagine that you will replace 2 everywhere in the cube description method. You get the here, you get the description here. This is going to equal to the content of you see the multiplicative the same space. Yeah. But I'm going to have a superpotential, which I haven't defined with it. Okay, so let's just say in this case what the superpotential looks like. Superpotential is really simple.
So you might want to say that this is related to your earlier story where compactifying on one side corresponds to adding superpotential for the opposite. So if
Right,
we,
yeah. There should be there should be also a decompactified, I don't know whether it's easier or harder version where I take the cross on this side. Should go to the okay. I'm tentatively to write this down because we haven't done the calculation yet for the multiplicative version, but that's like at least the expected answer. Where you view this additive version of the Coulomb branch as a subset of the multiplicative version, and then sorry, by the way, this is like an open, this is like an open subset in here because the base, as you can see, it's like a C star Y. Here the base was here the base is like C1. So it's so this is like an open subset here. So once you add more divided, partially compactified the stack here, that amounts to add a superpotential to a complement. I'm going to do it for this, yeah. The difficulty is actually lying as the diagonal. We can do, I'm going to state example for this as well. Yeah, I'm not going to do more general paper. It's like still under development. Yeah. The statement, yeah, the statement is true. You have even if you have a case 0 by some fundamental representation. Comes from that. Yes.
So you have the same group and same computation.
Yeah, same everywhere. So the only difference is that I put the multiplicative version here. It's potential. Yeah, I'm going to write down that. W in this n equal to in the middle n equal to 2 case is really easy to write down. It's just going to be well, I'm hesitating for writing this way.
the bottom segment general is to 80 quivers, but where every page is unique. One could in principle think about page groups which are non-linear stuff, then in fact, in 10 years, they will not involve in that.
But you don't change the same quiver, you say the next one.
That's right, for 80 quivers, the representation function.
Okay, so for middle n equal to 2, it's just most of this space. Oh, sorry. If I put a pure base thing, everything's are like smooth. If I add letters to it, then I need to do resolution and deformation on both sides.
Example for like silver signal and white. You have to like take whether.
Yeah, but here, okay. If I take it from the other part, that removes a lot of similarity.
Okay. For the other the potential also follows from like some kind of take a symmetry one that falls down.
No. So that's the new part. The superpotential is really interesting and new.
Okay.
So it's going to be I was writing and maybe might choose another one. So the one we actually worked out was using this superpotential like x1 minus x2 over y1 minus y2. So it differs from this by some multiplicative factor, which might change something. For GLN, yes, for GLN. It's going to be like sum over I from 1 to n. And on top, I'm going to write xi. And then bottom, I'm going to write j not equal to I, 1 minus 1j equal to 1. Actually, I think let's see this. Okay. So this is not a symmetrical product of the one-dimensional copy. So it's really twisted by the stack. And I think one can also have an interpretation of this guy coming from Grasslanian qualities. Okay, I'm just trying my hand here. You can correct that one. So when you compute this there's a closed GPO orbit that's just corresponds to P. So they corresponds to P minus 1. There's a dual orbit from here and it's P minus 1. P minus 1 has like this K fixed point towards fixed point. That has then towards fixed point that corresponds to here. And this denominator comes from this Lagrangian class, other class. So everything is like kind of a geometrical here, this connection.
It's not something to go on for.
Yeah, it's all of them. Yeah.
Yeah.
Yeah. We haven't figured that out yet. For this case, we know by hand what the resolution and the deformations are, and in general, with the multiplicative paper, we're still trying to we're going there. But haven't.
Well, I mean, we're depends what you're trying to do. If you're trying to prove homological mirror symmetry, then you need really every detail. So we haven't proven it exactly for arbitrary.
Well, maybe this is.
You want the statement?
You
First?
said the agreement.
Yeah.
So what would be the W?
It's going to it takes some time to actually write down the space. But then the double is actually it doesn't change from this. What we're changing is the space. The space will you have two sets of x's that satisfy roughly like you can write it explicitly what the state
Right, but I was hoping for some more abstract. Not in terms of code, but some code.
Yeah, but I don't know yet. In terms of maybe some side code.
So basically what we've done before, the space can be thought of as roughly as a you have to compare the mirror symmetry, the upside mirror symmetry, the downside mirror symmetry, where the downside mirror symmetry is talked about on the B side of the core of the Coulomb branch, and the core side that really supports both stable and blocks. Okay. And the fiber of that is so which is the whole multiplicative. The fiber of that is just a copy of C for the P side. How many C will be measured, right? Okay. And in some points, what mirror symmetry does is it's just fiber line mirror symmetry. All the stuff. So it's like mirror. The superpotential just tells you that for each copy of the C fiber with the C star action on it, we get the million mirror symmetry, equivariant mirror symmetry C with a C star action that scales homomorphic. So that's the you see, I mean, okay, so you can, to the extent that it's written, you can redefine Y, it's just some of that. That some of that X is mirror symmetry for C. If we just did mirror symmetry for C star, it would be like a multiplicative. There wouldn't be no X. But in our adding form range over the 3D theory involves copies of C from C star. So that's the thing. The simple that. And we have to.
I mean, ideal-wise, I agree with Mina. We need to write down detail and give some maybe geometric interpretation what it's should look like. Yeah. Would you?
Maybe
Yeah.
There are some other factors.
No other part.
Yeah.
Yeah.
So it's an important.
It's an important function. It's a new function.
Okay.
It's like people.
Is it like the potential sometimes you feel some people don't have to compute? Is it something?
Yeah, so this is the story is told in front upstairs. Okay. The downstairs it will be easy to write down what is the function W is, or it's even more elementary. And then those W, W with Anderson stuff. This the story that we're telling here is about nursing for the full Coulomb, not for the core.
Right, because there's something
well, you have to dress it some more with some more terms in superpotential, and then the critical add on some critical locals. This superpotential will get something that have been familiar representation here before, and maybe they remember that representation.
No, we don't know what it will come to. I don't know.
Yes, here is just U, right? So this example of the one word.
Yes.
That's U. So we have some, and then we need to.
Right. That's the general. Then you have the general formula for it.
But like for this, you still have like the points for U or.
Right.
So what superpotential will do, it will tell you exactly where your brains are allowed to put them. And the result of this particular rule about how the brains are allowed to fit will eventually tell you what your algebra is. And the algorithm.
As I remember, I don't remember all the detail. I remember the critical point. There's no ordinary critical point for this standard. Like if you want to think of a critical point, it happens at infinity. Yeah.
That's all. For the case of the pure gates. So in some sense, all the theory, in sense, there's probably the possibility. People talk about symbols, they'll think about superpotentials, but I like the critical point. This is maximal.
And also, so for JLM, so there are versions of this potential when you look at a lot of like on the development side. Like these are important. So you can put like some other phenomenon.
Sorry, say again.
So here, take the same formula that you have.
Yes.
That's replaced inside of power.
Power max.
Yeah. But this is still magic and it's still nice and it's still important. And okay. Here's like another set of coordinates on this. Doesn't do it, but you have like higher version.
That's right. The in principle you consider other things. However, the statement about this superpotential is going to give you mirror symmetry. Some other superpotential is going to give you none. Or it's going to give you mirror symmetry to make something exotic. You have to say, well, it's not just coherent sheets, it's like some coherent sheets be like objects with like other. So I think one of the story is that for anybody who's ever thought of mirror symmetry for the quintet, Okay, this is infinite. It's simpler because it's more rigid, it's more, from physics perspective, quantum theory is almost much more rigid than anything. And this is the case where mirror symmetry becomes a solvable problem. And it gives me, it gives you objects that are from a different computation theory. So that's what we're doing.
So shall we take a break?
No, let's not take a break.
Let's
Do you
do-
need a break?
I don't know, but
Okay. We just
if
took a break.
people want to.
We just took a lot of time.
Sure.
Tell us what you do.
Okay, so that's like the rough plan for trying to, or trying to make. So now I'm going to tell you the third layer in this story, which is the algebra, which is like, in some sense, we're cheating because we know what is the answer we want to get, and we try to say what's the object we're looking for. We're trying to match the maximum of one guy equals to the desired algebra, and this algebra, by some earlier result of Webster, is equivalent to covariance to this B side category. So that's like an unfair advantage we're having versus some earlier people where there's no very based algebra. But given that, still it's like non-trivial to prove. So try to prove the category has any relation with that. So let's see. At this later. Okay, so this algebra has 4 versions. Which you can, you can think of this as having a space of B side space, inside space. B side space we call that curly X, curly Y, and have a superpotential. We also have this it's not always the case that I have a B side space, in some cases, but we can always have the sKLRW. So the adjective have 2 adjectives. So A can be either planar or symmetrical, and B can be either additive or multiplicative.
Maybe we say cKLRW.
Yeah, sure. I should do that. A is Homological. L is Alga. R is PA. W is Webster. So I don't know exactly the history of this original KLR, but the matter saying that the KLR did something without matter in it, and Webster allows some matter to the game.
But anyway, the reason they were writing down these algebras is essentially they were motivated by questions of computation theory, in particular, categorization of quantums.
Right. I probably also should mention that's a practical state. That's like the best capital. As he wrote down some choosing bundles on B side and the momentum on that choosing bundle is supposed to be this sKLRW algebra. It's just this is like more explicit conventional. What is that?
We get cKLRW.
C, yeah, I'm going to explain. So C stands for the cylindrical, and P is for planar. And then I'm going to, go to the additive and the multiplicative. So So the usual fit for planar, like planar and additive. My y-sec space will map. So still, I'm just working with the pure gauge theory setting. Just those GL, those no matter. The theory generalizes, but just for simplicity of computation has to work with it. So here on the A side, it's y, it's over say points. It's going to be C cy plus star. So it maps to the symmetric. The planar here refers to the fact that cy is like a plane, not a system. And here, because we have additive, we have some W. It's not. We have non-trivial W. So W equals to and here, I'm not sure what space I should question.
That's probably what primary there.
Yeah, so this, yeah, I think if I'm understanding of the Xinjin's work is correct, prove that this is equivalent to so potential of multi. There are some further declarations. So she proved a much stronger result for general groups, not just for GL and for any redacted group have a result, but for GL, I think the like that. What is GL? Sorry, T is the towers in GL, W is the spectrum. Yeah, W is the message. Oh, okay. So it's 20,000. Yeah, well, it's not. So the strange thing is like the dimension is like half of the expected dimension. So that's why I'm hesitating to put a space here. But again, maybe my understanding of her work is wrong. And unfortunately, this is a recording, so my stupidity will be last forever. Anyway. So the planar and the multiplicative case. So into the same space. Why is the same space? Because but my W is going to be 0. I'm going to turn off this rotation. And here will be on the X side. X is going to be the equivalent of C star. Same X check because star. Sorry. Oh, sorry. I think I made a mistake.
Maybe we can focus on the interesting thing.
It's not interesting, but yeah. So so the whether I do additive or multiplicative, this just changes that what is potential or not on my base side. That just symmetrical. It just means like I put my y as a C star y cos it's like this part changes. So fiber over it's my power of system. So this here, this is the this cKLRW is going to be symmetrical and planar.
Wait, and here, this is the place where you do want to fill in the B side.
Yeah. And we have the B side. So I have this X. It's either going to be depending on the additive or multiplicative. We care about like additive case, so we have non-trivial potential. And X was asking for the let's see, cross start. And it's
Secrets.
yeah, secrets. I'm just using the okay. And then I take the horizontal parts, so it's mapped to Union of actually, I'm putting this X check to mean that the base of this map, the base of this guy maps corresponds to the fiber of the AP set. And the fiber of the B set corresponds to the base of the AP sets. On the mirror symmetry, there's some change of base and fiber. Right. This next. What is doing here? The base is C star, copy of C star. Here, the fiber is a copy of C star. Anyway, so what this algebra is all about? So let's just do some example. So in the case where we go to 2 with no matter, we have just a so-called cylindrical Newton-Hack algebra, which is a strand algebra that consists of motions of points connecting you fix two points on a circle, and you consider many ways to connect these 2 points. So you can have it's you can have like many ways. And you can also have dots. And there are certain computation rules. So you compose. There's a one important composition rule, which is following.
The position is a stacking boundary.
Right, computation is just seconds. And yeah, I know I use the red dot, which is the black dot, same thing. And if you have more strands, you can have this kind of the rules. Okay. So that's what's the symmetrical Newton-Hack 2 is about. You have 2 strands where you can move them around, and they have a fixed reference point on a circle. So you always have to go back to 2 circles, and you can have extra definitions of the dots. And the multiplication of the dots are like the commutative. And okay, there's also one very important thing where this equals to 0. If you straighten, you compose, if you straighten the strand, just disappearing background the composition.
And
So also related version of the Newman. So it's just the dot are moved on the just have things moving on the plane. There's no, it's not circling.
Maybe don't,
Yeah.
yeah, the beginning is in the end, but not the dots, so they just, maybe don't try to go back,
Yeah.
but they will back up. Wait for the beginning at the end.
So. Okay, so I have this simple version of this another algebra pure case case. So what do we actually need to prove? So we are selecting operator. Here is like a puzzle question. So for example, the n equals to 2 case. In the n equals to 2 case, we want to prove. So here I'm going to write down a local version of our main of the
Say what you want to show, maybe helpful dictionary, so that those strands of the cylinder mean what? You already know.
yeah, right. But that's like I'm having the answer right. Okay.
You're tired. Go on. Anyway, just tell us.
Sure. So the dictionary is like we want to show, and we want to show a Lagrangian. A Lagrangian, say T in our space Y2. So how do I define the space? How do I define this Lagrangian? So our space Y2 is fiber over the standard space Y2, which is a special square of this one. So the way this is T bar. Or maybe I do conditional notation curly T maps to a straight T here. So this straight T here is very easy to describe. Here it's and I just draw two disjoint straight lines in the base and take symmetric product. So that's like my thoughts there. Just copy out our cross. And upstairs, I can just alternatively say, okay, if I fix a point in Y2, which consists of 2 points in C star Y, then say this point lies on my Lagrangian, downstairs Lagrangian, then the fiber is just C star cross C star, because on the base diagonal, away from the diagonal, fiber is just C star cross C star, and then just put the straight line Lagrangian again upstairs on fiber. So that's going to be my curly T.
So these Lagrangians, the mirror to vector function.
Okay, so this if you want to say Blanchard system R to the fourth.
And this guy unique or something.
Yeah, this one looking at. But if you're alert, you're paying attention to the superpotential and say, wait a second, where's the superpotential? Let's stop here. Then I should tell you, okay, actually it's a little bit more subtle than that. Here's the stop, here's the stop. You want your Lagrangian to just come right before the stop, or we can say just align with the stop and it goes quickly. So as you move the base Lagrangian, as you move the base point, the stop will also move. And so you are more precisely saying, okay, you specify what your Lagrangian point, reference point, and then you parallel transport them along the base Lagrangian to define the fiber Lagrangian. So anyway, it's sort of topologically speaking, it's still hard to form. And because of the stuff, your parallel boundary has certain non-trivial transport. So that's T. And we need to show that the endomorphism of this Lagrangian equals to C. So that's the beginning of the story. Okay, so how do we actually prove it? There are two approaches. One is to do the hardcore discounting, which in principle is doable, but I'm just a beginner to learn discounting, so I run into some serious trouble.
There's a single bit on that.
Yeah, right.
Unlike the usual story where many here than one.
Yeah, so here, I say what's the two approaches. The first approach is that there's only one bad. There's only one man.
Still, before you talk about accounting, but they did intersection points to build pictures up there.
Right. Yes.
Then we'll think about that.
Right. So how do we compute the endomorphism of this people? So we're going to do this. We're going to be wrapping those in the base and fiber directions. So if I wrap my T, so let me use T. So wrapped T. So it's like. What does it look like? The base, it's going to be looks like parallel lines, but not wrapped. And on the fiber, so here, suppose this is like the fiber over some point. We also have some fiberglass wrapping. Not sure if this picture is clear or. So there's an easy dictionary to translate intersections into the diagram. There are some ambiguity, but there are certain part that's not ambiguous, which I will talk about. The easy dictionary is the following. So suppose here is my let me first show what is the identity. So I'm going to use red to mean my first slot. So curly T is going to be a form of the wrapped Lagrangian versus the original Lagrangian. So second slot T is my green guys stays put as a wrap, either in base or in fiber. My red guy wraps like this. So an intersection between the actual Lagrangian can be thought of as a tuples of intersection of this corresponding Lagrangian. So here, this pair corresponds to activity. And this pair,
Where identity of two strands on
yeah,
there.
the identity is like two strand that goes to that. And this kind of this 2 points, the first red strand goes to the second green guy, the second red guy goes to the first green guy. This corresponds to a crossing. me say the easiest crossing, say crossing the front. And you can also talk about for example, if I pick this intersection, but I left my right guy moves one positive in one direction, go here. Then I pick these two guys. Then that corresponds to like this diagram. So there's a dictionary between all the wrappings and all things. And you can also put in the dots, the fiber. So far, the fiber, I'm just not doing anything. Just taking a straight line. I'm taking the minimal, not doing anything. And you can also say over the identity point, I can take the fiber wrapping, like the wrapping line. As I two copies of the fiber again. I take this no wrapping and wrapping once. That corresponds to the dot on the second strand. So in the fiber copy, the fiber Lagrangian, basically each copy, because it's dot, is mirrored to a copy of C, or it's in the multiple outputs like C of C from it's like fiber in the wrong side. So you have the freedom to choose like how many wrappings you have in fiber direction. Okay. So so you can easily, by taking out combinations of the base intersection point and the fiber intersection point, you can hook up a vector space. Vector space, it is like this is universal. But that's far from you can claim victory because you have to match the composition. And that's where the pain begins. Because to match composition in the path side, you have to take 3 Lagrangians and count homological pieces. Here's now 1, now 2, here's now 1. You take an intersection, input intersection P1 from L1 to L2. You take another input intersection, from L1 from L2 to L3. And you can output intersection from L1 to L3. You can obtain that by counting how many pieces are there to mediate such output. Yes.
I don't do this when you count this for some variables.
Yeah, exactly. Yeah.
And you're right, I reached about recall variables.
Yeah. So we're in the lucky case where the category is like exact symplectic manifold. So where you can choose renormalization of the intersection points to absorb all the areas into the intersection points. So just an efficient count.
We also in a very lucky case where all the generators are zero. So instead of getting the main infinity category, that's sorted out. You don't even get mediated.
Yeah. In the lucky case, the only remaining task computing the time to the composition, it's still difficult.
But if you don't think this area is worried about what's about it?
No,
yeah, that's right. So
actually, in the complement of some diagram, it's true that there's the composition variation. It's sort of the obvious triangle on that triangle will give you a product. Say that you want us to do is Q.
okay, the difficult part is like this. So we need to reproduce this relation.
It's like that. In one complex dimension, symplectic geometry, it's really complex, just like a common triangle like that. Anybody can do it. In higher dimensions, it becomes more complicated. And the good thing is for us, it's almost everything comes from
Right. So
sorry.
right.
And actually, what is boss?
Okay, so here, okay, what is this bar here? So secretly, people have been setting bar equals to 1, so must want to return each bar to the game. So what is it?
Which you can by return. You can absorb it in a definition very thing, but it's actually conceptual is better to think of it.
So yeah, exactly. So if you deform the relation of the new head by introducing each bar in this particular relation, then you can ask, you can view this as a deformation by turning each bar to 0. So so we can so now. So you can see that why do we have an H bar is whenever you have your strand loses its identity. Like the first strand should go to here, but the first strand now goes to here. It's like in the class they do not know who is who. Like whenever you have this resolution of this crossing, you have a H bar factor. So we can compute easy. This one can be done in an easy way. So T, where we delete that. Let's define some Y-O. So Y-O is open line here, where you completely remove everything. It's Y1 equals Y. And another Y-O, we will package of that, the same superpotential. It can be written as CH2, say, H1 equals 0. If you delete the diagonal, there's no way you can, the strand cannot, let's say, there's no more resolution organisms allowed in this sense. Everything is easy and computable. But as soon as you try to put back this divisor, you need to count how many disks are there intersecting this divisor. That you want to put back some of the disk that does some part of the composition job to you. And then you need to count this. You need to get this relation. The trouble we work having is that, okay, when you try to build this composition, compose this two morphism on the planar side, we need to count how many times you have this parallel line.
We haven't said it correctly, right? So Y0 is we're removing the big diagonal, the actual diagonal, not virtual diagonal.
Yeah, this is the big diagonal. It's Y1 equals Y2.
Oh, okay. So you maybe like Y0 and this is not the base coordinate, these are the total coordinates, the big one, right?
Yeah.
Y0. Okay.
Yeah. So we need to compute how many times this as the output comes from these two input morphisms. We need to also compute how many times this guy, how many times this guy comes from this composition. And one need to prove that right here. One need to prove that these two numbers, A minus B, equals to 1. The trouble is that A and B themselves, they are not well defined. It depends on perturbation data. Sometimes you get 1 minus 0, sometimes you get 0 minus 1. And that's like the ambiguity. That's the very subtle ambiguity one needs to pin down. So the savior of the skein is, well, there are two saviors. But both of them come from this group of people. Okay. So one way is like you just work very hard on this problem and figure out the moduli space of the discounting and all that stuff, and figure out indeed no matter what perturbation data you have, you will get A minus B equals. The second way, which I like a lot, is to try to turn these Fukaya category intersection point into actual skein or strand in the three-dimensional Lagrangian. So maybe let me just draw a picture and then we can start. It's already too long. We'll get there. Yeah, I think this is the last part. So we're going to finish. So the approach to third intersection. So baby example. Consider of the stars that and mathematical like R, R2, standard R, S, or whatever. The star has. And if I take you, if I want to compute pulse from two laser fibers, if you find result of update and also some earlier results by people with initial AS works and the yes, yes. There's this they can compute this, they can turn this into pass from Q to Q. So what's the idea? The idea is the following. Suppose you have this Q prime, and you want to compute comes from one fiber to another fiber. But that happens by wrapping at near infinity, and like one Lagrangian intersect another. It's like intersecting point. Or equivalently, you can say you can send a report. And how do I get past down there on base Lagrangian? You are counting a disk. And the disk, well, maybe it's better to not use the reports. Have actual like a graphing. So here we have an actual result. Now we need to try to count the triangle, with one vertex of the triangle goes to the intersection, the other two goes to intersection. And the edge of this third edge of this will tell you the past distance. If that's the case, you have just a single column. Now, the data is very example. And also the Honda-Tian-Yuan. This is the following thing. For category, consider the symmetric product importation of its symmetric being of the Skein-Strand is not you want to understand the symmetric product as sort of a Hilbert scheme or something. And here, let's say it's a two-dimensional manifold. If I more one-dimensional manifold, that's called a fourth theory, but here's a pair here. So what they're doing is like they consider this multiple forms. Well, if we set Q equals to Q equals to Q prime, then you just get basically a group and we can do conversation there. Okay. So here, what they consider is like say T is TQ1 is the tuples of T1. It's the multiple coordinate fibers, destroy coordinate fibers here. And you can also compute another set of T prime. Okay. So these can be understood as k tuples of Lagrangian coordinate levels here. And then if you choose an intersection point up there, that will produce a k tuple of paths between the base point and that base point. Okay. And you can't claim victory yet because the trouble is that this map at the level of the path is not well defined. It depends on perturbation data. Depends on perturbation data. A simple example is the following: if I want to swap, say, in the case where k equals to 2. Say here's my Q1, here's my Q2, here's my Q1 prime, here's my Q2 prime. Suppose I'm trying to describe the path that goes like this. That actually can happen in two ways. You can actually have this guy goes very fast, and then this guy goes, or this guy goes very fast, and then this guy goes. It's like we have a red, green light, and which one goes first. If you want to draw this clearly in 3D, that exactly corresponds to an overcrossing or undercrossing ambiguity. And you do this, or you can do that. Okay. So that's some trouble if you want to just define it in a naive way. So the correct home is no longer the path. It's no longer the path space. The correct home is actually the path space modulo a relation, modulo the scheme relation. You will notice we have a similar view in our segment. The difference of two terms.
And not to say that this is based on the arrow versus based on verb and echo.
Right. So echo noticed that the same ambiguity comes when we count the Gromov-Witten invariant, where we have a single Lagrangian but a heterogeneous curve with boundaries on a single three-dimensional Lagrangian. And the only invariant counting is the Skein module of that three manifold. And here, our three manifold, the three-dimensional Lagrangian is going to be this M, which is two-dimensional, and cross a tangential. That's where actually the skein lives, the boundary of the skein. Okay, so for Honda-Tian-Yuan, their jobs then, they have a space that's symmetrical product of P star M, and they have a very nice description of the morphism of this multi-coordinate diagram. They can use this space to describe the affine algebra, that affine algebra. They have an easy, nice translation. But for us, our space is not symmetric P star M. That corresponds to having the full Hilbert scheme of points without deleting this important condition, indicating the vertical diagonal. So we have to do something extra, and that's something we're just currently doing. We have a prediction of how these things goes, how to multiply their star. We still need to prove that their whole technique has to factor through. So we end up with some subquotient of the story. Okay, thanks for your patience.
So I follow up on the generating converted for the I follow up on the generating converted for the so
what's the Lagrangian?
The
Yeah, it's supposed to generate a weight of I mean the Lagrangian, yes.
Yeah.
The predicted Lagrangian, yeah. So it's like a fiber Lagrangian. We have a space 31 next to the straight line.
Yeah.
I first to tell you what the Lagrangian I have on base.
Yeah.
Then I'm describing you for you what's the fiber is. First describing you for you like the fiber for a reference point. Then I'm going to parallel transport everywhere along that baseline.
Okay, so it's basically some kind of, okay,
It's awkward.
yeah, it's some, also,
Yeah, it's like
and what's the stop there?
yeah, the stuff. Yeah, right. So our superpotential fiber ones is the following. So the following form. So the W2 is a x1 over yeah, so in different versions, it doesn't matter. So for each the base point y1 and y2, these are just depends on x1 and x2.
Yeah.
Our fibers like this start square. So it's just a family of star square with the superpotential as coefficient depending on base. So you just look at a single fiber in the base space, it's going to be nearer to C2.
Okay, so that's one minus x2. Okay. And is it a vibration actually the y goes to the particular
It's not a vibration. There's a very hard to understand factor over the diagonal.
so it's still yeah, the diagonal.
Yeah, yeah.
Really put diagonal, then it's
Yeah, that's a very nice space. That's why it's easy to study away from if you delete the diagonal. Very easy to study.
and what the H bar comes, is it some area of
Yeah, H bar counts the intersection number with the vertical divisor.
H bar or A?
H bar, the power, H bar to the power. Yeah, remember it's like the intersection number of this with the y1, it's y2 back.
Okay. Okay, so okay.
Or you can say the shadow of this onto the diagonal.
Yeah. Okay.
Yeah. So maybe that's y1 into y2 is actually a subset in symmetric square of C1. So that's that. And then there are two ways to take it up. You can take the power transform or take the total transformation. Yeah. So let's say the cube to 1 plus. And you take the total transformation first. Or you can take the power transformation. And you know that you're using a tilde. So there are two possible ways. So so this is like so if I to define the horizontal part, I remove just the smaller guy. But there's still some left over from the big guy, which is like an exceptional divisor. Yeah. So we count this represents this part. Okay. Yeah. So it's also correct. It's like the true diagonal, the remaining part.
So it's so you have to use it for.
Yeah. So this guy looks like some divider with some like vertical fiber. This guy is just the vertical fiber. When we remove that, we just get the P1 is equal to this like yes. But all that has to do with decision.
Is there a usual back on here?
Oh, you have to carry that to express that given.
Okay, well, yeah, because I know these I mean, I read Webster's papers on KLR algebras, where you're trying to categorize like quantum curves, and it's just really weird that you're getting symmetric.
Yes, so the statement is that A branes and B branes correspond to modules of quantum.
Okay.
And the homes between them morphism in the category.
Okay, so these are all quantum, right?
So that is the equivalence of the radical.
Okay, I see.
So if I walk away from this talk thinking like, you know, fancy model and homological mirror symmetry is just some basic representation theory of cKLRW, rather than having missed the point, is that there.
But these very special statements, yeah, but you know, yeah, like some very smart people came and wrote them down. In some sense, when they think something beyond it, also physics, and they have some kind of deeper meaning. They couldn't have been anything else.
That's a follow-up question. So, there are these instructions for getting 3D topological molecule theories from string theory and time theories, specifically, but all of those examples that they give up with are the transformers use, and they were enhanced, but what they came to believe that you start with cKLRW algebra and you have secretly there's nothing like that.
I mean, it's nice sort of construction of logical filters, and then you would start asking questions, and then probably like even though this construction does not the connection to ordinary time series is really there's not really a shadow, right? This is more than that. It's like one big crazy time and only that. But in principle, it would play the same way for their before. Ask what the bar question. There might have easier kind of verification to do by having lower confidence. But the way an ordinary time period comes out of something is hard enough to get that is hard enough.